Have you ever looked up at the night sky and felt a deep, inexplicable sense of wonder? Those countless stars scattered across the velvet blackness evoke a profound question that has captivated human imagination for centuries. Are we alone in the universe? This question is more than philosophical or poetic. It's scientific and deeply puzzling. Given the vastness of the cosmos, the billions of stars within our own Milky Way galaxy, and the trillions of galaxies beyond, it seems almost certain that life must have arisen elsewhere. And yet, despite decades of searching for signs of extraterrestrial intelligence, we have found nothing definitive. This silence is what scientists call the Fermi Paradox, a glaring contradiction between the high probability that alien civilizations exist and the total lack of evidence or contact with any of them. To grasp the weight of this paradox, we first need to understand the scale of the universe and what it means for the potential for life. Our Milky Way galaxy alone contains roughly 100 billion stars, each potentially orbited by planets. Modern astronomy has revealed that planets are common, and many lie in the so-called habitable zone, where conditions might allow liquid water to exist, a fundamental prerequisite for life as we understand it. Recent discoveries by missions like the Kepler Space Telescope have identified thousands of exoplanets, many potentially Earth-like, increasing our confidence that habitable worlds abound. But the Milky Way is just one galaxy among billions. The observable universe contains an estimated 2 trillion galaxies, each filled with billions or trillions of stars. This staggering number means there could be an unimaginable number of planets capable of supporting life. It is hard to overstate how huge these numbers are. When we combine the vast number of potentially habitable planets with the 13.8 billion years age of the universe, plenty of time for life to evolve and civilizations to arise, it seems nearly impossible that Earth is the only cradle of life. Yet, despite this apparent abundance of opportunity, we have no confirmed evidence of extraterrestrial life, let alone intelligent civilizations. The silence is deafening. This contradiction was famously summed up by physicist Enrico Fermi in 1950 when he asked, "Where is everybody?" During a casual conversation at Los Alamos National Laboratory, Fermi's question captured the essence of the paradox. If intelligent life is common and has had millions of years to develop technology and explore the galaxy, why haven't they contacted us or left detectable signs? Scientists and philosophers have wrestled with this question for decades, offering a wide range of possible explanations, from the rare occurrence of life to the inevitability of self-destruction, from advanced civilizations hiding their presence to fundamental misunderstandings of the nature of life and intelligence. To explore these ideas, it's important to first look at the framework that scientists use to estimate the likelihood of extraterrestrial civilizations, the Drake equation. Proposed by Frank Drake in 1961, this equation attempts to quantify the number of active, communicative civilizations in the Milky Way by multiplying several factors: the rate of star formation in our galaxy, the fraction of stars with planetary systems, the number of planets that could potentially support life, the fraction of those planets where life actually arises, the fraction of life that becomes intelligent, the fraction that develops technology detectable from space, and finally, the length of time such civilizations release detectable signals. While many of these factors remain unknown or highly uncertain, the Drake equation provides a useful conceptual tool to frame the problem scientifically. Even with conservative estimates, many calculations suggest that there should be dozens, if not hundreds, of civilizations in our galaxy alone. This makes the silence all the more puzzling. One possible explanation is the rare Earth hypothesis. It suggests that while microbial life might be common, complex, intelligent life is extraordinarily rare. This could be because the combination of factors needed for complex life is extremely unlikely. Earth has many unique characteristics: a large moon that stabilizes its axis and climate, plate tectonics that recycle carbon and regulate temperature, a magnetic field that shields from harmful solar radiation, and just the right chemical composition. All these factors might be crucial for complex life, and it's possible that few planets have such perfect conditions. Another school of thought revolves around the idea of the Great Filter, a concept suggesting there's some critical stage in the development of life that is very difficult to surpass. This filter could lie behind us, implying that the emergence of intelligent, technological life is an extraordinarily rare event. Alternatively, the Great Filter could lie ahead of us, meaning that advanced civilizations tend to self-destruct through warfare, environmental collapse, or technological catastrophe before they can colonize the stars or communicate across interstellar distances. This leads to a sobering perspective on humanity's future. If the Great Filter lies ahead, then our civilization might face existential threats that could prevent us from reaching out into the cosmos. If the filter lies behind, then we might be one of the lucky few to have made it this far, an incredibly rare occurrence in the universe. Other theories suggest that intelligent civilizations might exist but choose to remain silent or hidden. The zoo hypothesis imagines that extraterrestrial civilizations are deliberately avoiding contact with us, observing humanity like zookeepers watch animals, waiting until we reach a certain level of technological maturity or social development before revealing themselves. This idea raises questions about the ethics of contact and whether advanced beings might see interference as harmful. Another possibility is that we simply haven't been looking or listening in the right ways. Our current methods for searching for extraterrestrial intelligence focus heavily on detecting radio signals or laser emissions, but it's possible that alien civilizations use entirely different means of communication, maybe quantum entanglement, neutrino beams, or other technologies beyond our understanding. Alternatively, they might deliberately avoid broadcasting signals to prevent detection. Timing also plays a crucial role. The universe is billions of years old, and it's possible that civilizations have risen and fallen long before humanity existed. The cosmic timing problem suggests that intelligent life could be extremely rare at any given moment, and that we might be among the first, or among the last, technological civilizations in the galaxy. More speculative ideas abound, ranging from the notion that aliens are already here but concealed by advanced technologies, to the simulation hypothesis, the idea that our entire universe is an artificial construct created by a higher intelligence, and the absence of aliens is simply part of the simulation's design. The Fermi Paradox forces us to confront fundamental questions about life, intelligence, and our place in the cosmos. It challenges us to think deeply about the nature of existence and the future of humanity. Will we be alone forever? Or will we one day hear the long-awaited signals from other stars? Until then, the paradox remains one of the most profound mysteries in science. Continuing our journey through the Fermi Paradox, let's delve deeper into some of the most intriguing explanations and what they mean for us. One key factor to consider is the nature of life itself and the possibility that life might be far more common, but intelligence, especially the kind capable of interstellar communication, might be incredibly rare. While the emergence of simple, microbial life might be a natural consequence of chemistry and planetary conditions, the path from single-celled organisms to intelligent beings is a long, complex, and uncertain process. On Earth, for roughly 2 billion years, life consisted solely of microscopic organisms. Multicellular life only appeared around 600 million years ago, and it took until about 300,000 years ago for Homo sapiens to evolve with the intelligence and technology we have today. If Earth's timeline is typical, it suggests that intelligent life is not inevitable, but the result of a highly improbable chain of evolutionary events. Factors such as mass extinctions, environmental changes, genetic mutations, and chance all shape the path of evolution. It could be that on most worlds, life never progresses beyond simple forms, or intelligent species fail to develop complex technology. This perspective reduces the expected number of advanced civilizations dramatically. Yet, if intelligence is so rare, it raises a paradox of its own. Why then does life appear to have emerged so quickly on Earth after its formation? Some scientists argue that once conditions are right, life might spring up readily, suggesting microbial life could be widespread, even if intelligent life is rare. This has led to the idea that we might find microbial life elsewhere in our solar system, perhaps beneath the ice of Jupiter's moon Europa or Saturn's moon Enceladus, or in the soil of Mars. Discovering even simple life beyond Earth would be monumental and could help answer some aspects of the Fermi Paradox by confirming that life arises readily. Another possibility is that advanced civilizations do exist, but do not expand aggressively through the galaxy. The assumption that alien civilizations would colonize the stars, spreading rapidly like human explorers or conquerors, might be flawed. Perhaps technological civilizations prefer sustainability, or their values differ greatly from ours. They might focus on virtual realities, inward exploration, or other pursuits that do not involve visible colonization or broadcasting signals. The question of communication is central. Humans have been actively sending radio signals for about a century, a cosmic blink of an eye. It's possible that civilizations develop communication technologies that become undetectable over time, or that they communicate in ways we cannot perceive. For instance, signals might be highly compressed, encrypted, or transmitted in forms not yet understood by our instruments. The search for extraterrestrial intelligence, known as SETI, has employed numerous methods over the decades. These include scanning the sky for radio waves, searching for laser pulses, looking for megastructures like Dyson spheres that might surround stars, and even monitoring unusual astronomical phenomena. While no confirmed signals have been found, the search continues, growing more sophisticated with new technologies and larger data sets. One intriguing concept is the idea of self-replicating probes, also known as von Neumann probes, which an advanced civilization could send to explore and colonize the galaxy. These probes would use local resources to build copies of themselves and spread exponentially. If such probes existed, we might expect to have detected them by now. Their absence deepens the mystery and fuels speculation about why the galaxy seems so quiet. Another important aspect of the Fermi Paradox is the possibility that civilizations face existential threats before they can spread. The Great Filter theory highlights risks such as natural cosmic disasters, pandemics, or technological self-destruction. Humanity faces its own challenges today, from climate change to nuclear weapons and emerging technologies with unknown risks. Our survival might depend on overcoming these challenges to join a potential galactic community. Philosophically, the Fermi Paradox invites reflection on what it means to be intelligent life. Are we unique in the cosmos? What responsibilities do we have as possibly the first or only advanced civilization? The paradox also touches on hope and fear. Hope that we are not alone, and fear that the silent signals doom for civilizations that have come before us. Some scientists advocate for increased efforts to communicate outwardly, a practice called METI, messaging to extraterrestrial intelligence. This approach is controversial because it raises concerns about attracting unwanted attention. If there are hostile civilizations out there, broadcasting our presence might be dangerous. The debate over METI reflects the uncertainty inherent in the Fermi Paradox. The paradox also drives innovation in science and technology, pushing us to develop new ways to search and explore. Missions to Mars, Europa, and other bodies in our solar system aim to detect signs of life. New telescopes like the James Webb Space Telescope help characterize exoplanets and their atmospheres, searching for biosignatures or technosignatures, signs of life or technology. The vast distances and timescales involved pose enormous challenges. Even if we detect a signal from a civilization hundreds or thousands of light years away, the time it takes for messages to travel means real-time conversation might be impossible. This forces us to rethink what communication and contact might look like on a cosmic scale. The Fermi Paradox is a profound and multifaceted mystery that touches on astronomy, biology, technology, philosophy, and the future of humanity. It challenges us to continue exploring, searching, and questioning, and reminds us of the fragility and preciousness of life in the vast universe. Building further on the Fermi Paradox, it is essential to consider how the nature of technology and the development of civilizations might shape their detectability and longevity. One prominent idea is that advanced civilizations may quickly transition to forms of existence that are fundamentally different from what we expect or can observe. For instance, a civilization might develop artificial intelligence or digital consciousness, migrating away from biological forms into virtual realities. Such post-biological entities may have no need or desire to communicate using electromagnetic signals or to physically explore the galaxy. Their activities could be confined to dense computational environments, making them effectively invisible to our traditional search methods. This leads us to consider the concept of the transcension hypothesis, which suggests that civilizations evolve toward increasingly dense, compact, and efficient forms, possibly within black holes or other exotic environments. These civilizations might no longer interact with the external universe in ways that we can detect. If this is true, it would mean that intelligent life is abundant but cloaked in forms beyond our current scientific reach. Another intriguing possibility is that of interstellar isolation by choice. Civilizations might deliberately avoid contact for ethical, strategic, or practical reasons. For example, they might fear contamination of their own culture or ours, or they may have strict non-interference policies, akin to the Star Trek Prime Directive. They might regard younger civilizations like humanity as not yet ready for contact, or potentially dangerous. This self-imposed isolation could explain the silence, advanced beings watching from afar but not making their presence known. The cultural and psychological factors shaping an alien civilization's behavior are, of course, speculative, but they remind us how much our own perspectives influence our assumptions. It is tempting to project human motives onto extraterrestrials, imagining they would act like explorers, conquerors, or communicators. But the vast diversity of possible life forms, environments, and histories suggests we should be cautious in making such assumptions. Another angle on the paradox is the idea that we are simply not looking hard enough or in the right places. Our search for extraterrestrial intelligence has so far been limited in scope and duration, covering only a tiny fraction of the sky and radio frequencies. We are just beginning to develop the technology needed for a comprehensive search. Projects like Breakthrough Listen are scanning millions of stars for artificial signals, but given the scale of the galaxy, the search is still in its infancy. Moreover, many astrophysical phenomena can mimic or mask potential signals. Natural radio bursts, cosmic noise, and instrumental artifacts complicate the search. Distinguishing between natural and artificial signals is a huge challenge. There might even be messages or signals in data we have already collected but have not recognized as artificial. One often overlooked possibility is that intelligent life might exist but use communication methods so advanced or subtle that we cannot detect them. For example, they could communicate using neutrinos, gravitational waves, or quantum entanglement, all fields still emerging in human science. If such technologies are common among advanced civilizations, our radio-based searches would be ineffective. Furthermore, civilizations might use communication that is localized and non-leaky, meaning they do not emit signals into space but rely on direct, secure communication methods. This would keep their presence hidden from outside observers like us. The Fermi Paradox also raises questions about the longevity of civilizations. Even if intelligent life arises frequently, civilizations may be short-lived on cosmic timescales. Technological societies could self-destruct, be destroyed by natural disasters like asteroid impacts or supernovae, or lose interest in exploration and communication. This leads to a cosmic graveyard where extinct civilizations leave few or no traces. From this perspective, the galaxy might be littered with ruins of long-dead civilizations, their signals faded or erased by time. Searching for technosignatures beyond just signals, such as waste heat from megastructures or unusual atmospheric gases on exoplanets, is an expanding field. It may help detect remnants of civilizations that no longer exist. There is also the intriguing concept that the universe might be fine-tuned for life and consciousness in a way that makes it inherently difficult for civilizations to expand or communicate across vast distances. Physical limitations such as the speed of light, energy requirements, and cosmic expansion might impose insurmountable barriers to interstellar travel and communication. These constraints might lead civilizations to focus inward rather than outward. One of the most fascinating, if unsettling, interpretations of the Fermi Paradox is the possibility that we are truly alone, that Earth is the only place in the universe where life, especially intelligent life, has emerged. This would mean that humanity carries the unique responsibility to preserve and cherish life, and perhaps to spread it ourselves. It also raises profound philosophical and spiritual questions about the meaning and purpose of life. Alternatively, if the universe is teeming with life but silent, it might indicate that advanced civilizations have evolved beyond our understanding, or that the universe itself operates under rules that limit contact. The Fermi Paradox remains an open question, inspiring scientific inquiry, philosophical reflection, and creative speculation. It reminds us that despite our advances, much about the universe remains mysterious. It challenges us to expand our thinking, develop new technologies, and approach the cosmos with humility and curiosity. As we continue to explore space, develop better telescopes, send probes to other worlds, and analyze data, the answer to the paradox may come in unexpected ways. Whether we find microbial life in our own solar system, detect signals from distant stars, or realize we are truly alone, the journey promises to reshape our understanding of existence. Ultimately, the Fermi Paradox forces us to look not just outward into the stars, but inward at ourselves, our nature, our future, and the choices we make as stewards of life on Earth. It's a profound reminder of how precious and fragile life is, and how much remains to be discovered in the silent cosmos. As we move deeper into the enigma of the Fermi Paradox, it is worth exploring how our own technological and societal evolution might influence our ability to detect or be detected by extraterrestrial intelligence. Humanity is at a unique crossroads in history, transitioning from a species confined to Earth to one that aspires to explore and colonize other worlds. Our advances in technology have allowed us to send robotic explorers to Mars, probe the outer planets, and even glimpse planets around distant stars. We have built powerful telescopes capable of analyzing the atmospheres of exoplanets for potential signs of life, and we have developed projects like SETI to listen for signals from other civilizations. Yet, our own radio and television broadcasts, which unintentionally leak signals into space, are already fading as we shift toward more efficient, less broadcast-intensive communication technologies like fiber optics and satellite relays. This means that the radio bubble around Earth might be shrinking, reducing our visibility to distant observers. This raises the intriguing possibility that many civilizations might have a short window during which they emit detectable signals before becoming effectively invisible. The timeline for technological evolution may also differ greatly between civilizations. Some may develop radio technology early, but quickly move on to other forms of communication, while others might never develop detectable technologies at all. The chances of overlapping with another civilization's window of detectability might be very slim. This brings us to the question of interstellar travel and colonization. Science fiction often imagines civilizations spreading rapidly through the galaxy, but the realities of physics impose severe constraints. The vast distances, limited by the speed of light, mean that even traveling at a significant fraction of light speed, it would take thousands or millions of years to traverse the galaxy. This immense timescale might discourage or limit expansion efforts. Moreover, the enormous energy requirements and potential dangers of interstellar travel might make it impractical for many civilizations. They may instead focus on their home systems or virtual worlds, abandoning the idea of galactic colonization. Alternatively, they may develop technologies like wormholes or faster-than-light travel, but these remain speculative and unproven. The question of motivation is equally important. Would alien civilizations feel compelled to explore, colonize, or communicate? Their cultural, ethical, and psychological makeup could differ dramatically from ours. They may prioritize sustainability, social cohesion, or inward exploration rather than expansion. Understanding these possibilities requires us to rethink anthropocentric assumptions, but on the other hand, if civilizations do choose to explore and colonize, why have we not observed any signs of their activity? The concept of a galactic club, a network of civilizations coordinating contact and exploration, remains hypothetical. If such a club exists, they may impose strict rules about contact with emerging civilizations like ours. Alternatively, the silence might indicate a great silence or cosmic quarantine, where advanced civilizations avoid interfering with younger civilizations. This idea suggests a universe filled with life, but governed by unspoken rules to preserve natural development. From a scientific standpoint, the search for life and intelligence is becoming more diverse and sophisticated. Beyond radio signals, researchers look for technosignatures such as unusual chemical compositions in planetary atmospheres, large-scale engineering projects like Dyson spheres, or laser emissions. Future missions may deploy probes to nearby star systems, looking for physical evidence of extraterrestrial technology or artifacts. Astrobiology, the study of life in the universe, is a rapidly growing field. By understanding the extremes of life on Earth, from deep-sea vents to acidic lakes and frozen deserts, scientists expand the range of environments where life might exist elsewhere. This informs the search for life on Mars, Europa, Enceladus, Titan, and beyond. The Fermi Paradox also intersects with philosophy and theology. It challenges long-held beliefs about humanity's uniqueness and place in creation. It forces us to grapple with existential questions about meaning, purpose, and destiny. Are we a cosmic accident or part of a grand design? Is silence a sign of isolation or a call to stewardship? Moreover, the paradox reminds us that the universe is vast and ancient, and that humanity's current stage might be just a fleeting moment. It humbles us, emphasizing how much we do not know and inspiring curiosity and humility. As we stand on the brink of becoming a spacefaring civilization, the Fermi Paradox serves as both a warning and a beacon. It warns of the risks and challenges we must overcome, technological, environmental, and ethical, to survive and thrive. At the same time, it beckons us to explore, discover, and connect. In conclusion, the Fermi Paradox is a profound mystery that touches on science, philosophy, technology, and human destiny. It challenges us to expand our horizons, develop new tools and ideas, and embrace the unknown with courage and hope. Whether we find others or remain alone, the quest to understand our place in the cosmos is one of humanity's greatest adventures. To further deepen our understanding of the Fermi Paradox, let us explore the possibilities regarding the nature of extraterrestrial civilizations themselves and their potential impact on the observable universe. One compelling theory is that the absence of contact or evidence might be due to the inherent difficulties and dangers in sustaining a technologically advanced civilization. Civilizations might undergo what is known as the Great Filter, a series of critical evolutionary or technological hurdles that are extremely hard to overcome. This Great Filter might lie in our past, such as the emergence of life from non-life, the evolution of intelligence, or the development of complex technology, or in our future, such as the avoidance of self-destruction. If the Great Filter is ahead of us, it implies that many civilizations fail to survive long enough to become visible across interstellar distances. This sobering thought highlights the urgency of addressing existential risks on Earth, including climate change, nuclear conflict, and emerging biotechnologies. On the other hand, if the Great Filter is behind us, it would mean humanity is extraordinarily rare and possibly unique in the observable universe. This would make the responsibility of preserving life and spreading it even greater. It would also provide an answer to the Fermi Paradox. Intelligent life is so rare that we may never find evidence of others. Another hypothesis to consider is that of zoo hypothesis or planetarium hypothesis, which suggests that advanced extraterrestrial civilizations deliberately avoid contact with us to allow natural development. In this analogy, Earth and humanity might be part of a vast cosmic wildlife preserve or an elaborate simulation where we are observed but not interfered with. While speculative, this idea forces us to consider the possibility of surveillance or observation beyond our detection. Further complicating the paradox is the notion that we may not be looking for the right signs or in the right way. Our technological and conceptual tools are limited by our human perspective. For example, extraterrestrial intelligence might manifest in forms so different that we cannot recognize them as life or intelligence. They might communicate through methods that are unrecognizable, or their civilizations might be based on entirely different physical or chemical principles. Additionally, some theorists have proposed that the universe itself may be a simulation, with the apparent silence and lack of contact reflecting programmed constraints. While this idea ventures into philosophical and metaphysical territory, it has gained some attention due to advances in computational theory and digital physics. In terms of practical steps, humanity's efforts to detect extraterrestrial intelligence have expanded greatly. Large-scale surveys using radio telescopes like the Allen Telescope Array and the Square Kilometre Array aim to scan broad swaths of the sky for anomalous signals. Optical SETI looks for laser pulses that might indicate deliberate communication. Researchers are also examining fast radio bursts and other unexplained astronomical phenomena as potential technosignatures. Meanwhile, the discovery of thousands of exoplanets, some within their star's habitable zone, has energized the search for life. Missions like Kepler, TESS, and upcoming telescopes provide critical data on planet size, orbit, and atmospheric composition. Finding biosignatures such as oxygen, methane, or industrial pollutants would revolutionize our understanding of life in the cosmos. The paradox also informs the design of interstellar probes and potential future missions. Concepts such as Breakthrough Starshot envision sending tiny, laser-driven spacecraft to nearby stars at a significant fraction of light speed. While still conceptual, such missions could one day provide direct exploration of exoplanets and possibly detect signs of life or technology firsthand. Beyond science and exploration, the Fermi Paradox inspires cultural reflection. It challenges writers, artists, and thinkers to imagine futures and civilizations different from our own. It fuels science fiction, which in turn influences scientific thinking and public interest. Finally, the Fermi Paradox is a powerful reminder of the interconnectedness of life, technology, and the cosmos. It highlights the fragility of civilization and the need for cooperation and foresight. As we look to the stars, the paradox encourages us to cherish our planet, nurture our biosphere, and strive toward a future where humanity can thrive among the stars. Whether or not we find company, as we bring this exploration of the Fermi Paradox to a close, it's important to reflect on the broader implications for humanity's future and our place in the universe. The paradox not only poses scientific and philosophical questions, but also serves as a mirror reflecting our hopes, fears, and aspirations as a species. One key lesson is the importance of sustainability and long-term thinking. The Great Filter concept reminds us that civilizations may be fragile and prone to self-destruction. Climate change, resource depletion, nuclear proliferation, and uncontrolled technological advances all pose existential risks. Overcoming these challenges may be a prerequisite for joining a potential cosmic community. Moreover, the paradox urges us to advance the search for life and intelligence with humility and openness. As our technology improves, we must expand the range of phenomena we examine, embrace interdisciplinary research, and consider novel hypotheses. This includes developing better instruments to detect biosignatures and technosignatures, investing in space missions, and fostering international cooperation in the scientific community. The question of whether to send messages into space is both practical and ethical. Messaging to extraterrestrial intelligence, METI, initiatives face debates about potential risks and benefits. Some argue that active outreach could invite contact and collaboration, while others caution about unknown dangers. Navigating this balance will require careful thought and global consensus. Philosophically, the Fermi Paradox invites us to reconsider what intelligence means and how it might manifest. It challenges anthropocentric views and encourages humility about our assumptions. The universe may be more diverse and complex than we imagine, and our definitions of life and intelligence may need to evolve. Spiritually, the paradox can inspire a sense of awe and connection. Whether or not we find others, recognizing the vastness and mystery of the cosmos can deepen our appreciation for life on Earth and our shared humanity. It can motivate stewardship of our planet and a commitment to exploring the unknown responsibly. Finally, the Fermi Paradox is a call to curiosity and exploration. It embodies the essence of scientific inquiry, the quest to understand our origins, our destiny, and the nature of existence itself. As we continue to gaze into the night sky, seeking answers, we participate in a timeless human journey that transcends borders and generations. In closing, the Fermi Paradox remains one of the most profound mysteries confronting science and humanity. Its questions challenge us to push the boundaries of knowledge, to embrace uncertainty, and to imagine a future where we are not alone, or where our solitude carries a unique significance. Thank you for joining this deep dive into the Fermi Paradox. May this reflection inspire wonder, critical thinking, and a lasting fascination with the universe we call home.